All right, welcome back. So we're gonna try example number 3. We're given a function, and this is 6 times the quantity x minus 2 raised to 2/3 power. So we'll begin by finding where the function is increasing, decreasing. So to do that, we need to begin by finding the derivative, right, and find the critical numbers, right. So I'll label them here. We find x values when find the x values such that the first derivative is 0 or the first derivative is undefined. Right, so we're gonna find, let's find out, let's take the derivative of this first. First derivative of this, we can see here that we have a function inside a power function, so we have to use chain rule. So bring down the power of 2/3, leave the inside as it is, and then subtract 1 from the power. 2/3 minus 1 is going to be negative 1/3, right? You can just do that in your head or by hand. You can type it in your calculator. This will give you negative 1/3. Right, so, and then multiply by the derivative of the inside. The derivative of the inside is going to be 1 for x and 0 for the negative 2, for the minus 2. So this sort of kind of like goes away, right? So let's just simplify this. 6 times 2/3 is going to be, well, 3 goes into 6 2 times. So 2 times 2 is 4 times 1 is 4. So we have 4 times x minus 2 to the negative 1/3, right? And we can also rewrite this in a fraction form because this has a negative power. We're going to move that factor to the denominator. So the factor that has the negative power is moved to the denominator. There you go. And so this is our derivative. So let's figure out whether can this equal 0, right? So well, the only way this can equal 0, the only way this can equal 0 is whenever the numerator is equal to 0. But that's not possible. 4 cannot equal 0. So that means that this cannot happen, right? This cannot happen. So the next case is which is very rare, right? That we actually do this one, but we have to do it. Is whenever the first derivative is undefined. So when will this be undefined? Well, it's sort of kind of neat, right? Because at this one, you look at the numerator when it's 0. At this one, you look at the denominator. Is equal to 0. So look at the denominator and find when this will equal 0. So so this only way that this is going to be undefined here is whenever the bottom is 0. So we take the denominator and find out when is going to be, when the denominator will be 0. In other words, find the x that makes the denominator be 0. So that isolates the process to just do, oh, we just have to find out when is this going to be 0. So we can argue that this is going to be 0 whenever the inside is 0, or you can just say, oh, well, this is the same thing as if we raise the power of both sides by 3 to undo the power of 1/3. So that means x minus 2 equals, well, 0 to the third power is still going to be 0, and these cancel each other out. So now we can proceed by finding x equals 2. And there you go. So we just got to make sure that this is going to be a critical number. Check whether this is a critical number, and it is because it is part of the domain, right? In other words, if you plug in positive 2 in here, 2 minus 2 gives us 0. 0 to the third power, 2/3 powers is still 0. 0 times 6 is 0, so this gives you 0, which is a real number. So yeah, so this is not just, this is actually in fact a critical number, right? Right, so we found a critical number. Well, we need to figure out what the question was, whether this is going to be increasing or decreasing. So at this point, we can just create a number line, and we have positive 2 to separate to subdivide this number line. So whenever x equals 2, the derivative will be 0. So let's circle that one. So all we have to do is figure out what's happening on the left side of 2 and on the right side of 2. And of course, I always try to use 0 as much as I can, because it's always easy to compute with or work with. So let's look at the first derivative. So what happens when you plug in 0 in there? Well, the 4 is a positive. When you plug in 0 for x, you get 0 minus 2 is negative. Negative to the 1/3 power is still going to be negative. So positive or negative is negative. And then when you plug in 3, 4 is positive. And then for when you plug in 3 here, 3 minus 2 is going to be 1. 1 to the 3rd power is going to be positive 1. So in other words, a positive number. And remember that all we care is whether these are positive or negative, because we know that translation is, if your derivative is negative, that means your function is decreasing. And here I made a boo-boo, right? So what I meant here is this is not a 0, right? This is not a 0. Made a silly mistake here. This actually is undefined, right? I think because we always end up getting critical number that are zeros. I made a silly mistake, which in my notes it says undefined, but of course I didn't check my notes. So it's undefined. Maybe I'll write myself a note here, undefined. And so now we have to look at what is when the derivative is positive, your function is increasing. There you go. So there you go. So we found that the function is decreasing from negative infinity all the way to 2. And so decreasing from negative infinity to 2. And is increasing from 2 to positive infinity. Increasing from 2 to positive infinity. And that's all they asked to find, right? So this box this out, and we have our solution here. All right, so let's jump into part B. Part B is asking us to find where is the function concave up and concave down. For this, I remind you that we're looking at the second derivative when it's 0 or when the second derivative is undefined. Right, we're looking for the x values when that happens. So first of all, let's jump in and take the second derivative. I'm going to write down the first derivative first. That way we can kind of have it visualize it here. And what I'm going to do here is I'm going to keep it in the regional derivative that we had before we move the factor x minus 2 to the denominator. The reason why is because it's easier for us to find the derivative using product rule, or the constant multiple rule. So it's easier for us to do it here. So let's go ahead and do that. So we have to use the chain rule because we have a function inside the power function. So what do? We take the derivative of this using chain rule by bringing the power down and multiplying by 4. So that's 4 times negative 1/3 times x minus 2. Leave the inside as it is, and then subtract 1 from the power. Negative 1/3 minus 1. Negative 1/3 minus 1 is going to be negative 4/3. And that gives, and then times the derivative of the inside, which is 1. All right, so if we simplify this, this will give us negative 4 over 3 times x minus 2 to the negative 4/3. And because this has negative power, why don't we move this factor down, right? So we have negative 4 in your numerator, and the denominator we have the 3 multiplied by x minus 2 to the positive 4/3, right? um, this automatically gives us changes to a positive sign, right, on your power. And there you go, right? So now we have to figure out whether what kind of possible points of inflection we're going to have here. So we can kind of see here real quick that this is not going to work out, right? This one's not going to work because in order for this to equal 0, the numerator needs to equal 0, right? And obviously negative 4 does not equal 0, so there's no case for this. So instead, we have the other alternative, and that is when f double prime is undefined. And that's going to happen. That's going to happen whenever the denominator is equal to 0. So take this and set it equal to 0. So let's take 3x minus 2 to the 4/3, set it equal to 0. We can set we are dividing both sides by 3, right? And then taking the a power, right? I always show you guys that the only way that this is going to equal 0 is whenever the inside is 0, because 0 to any power is going to be 0. This cannot be any other number than 0. So x minus 2 equals 0, which implies by adding 2 it equals 2. All right, so that's your possible point of inflection, and we're going to use this to help us find the number line, right? So here's our number line at 2, and what we need to know is what has happened to the second derivative. Well, we know what happens when x equals 2. The second derivative will be undefined. What we need to figure out is what happens around 2. So 0 and 3 are good possible choices. So let's go ahead and test these numbers. So let's write the second derivative function. Okay. So again, I want to show you guys how to be more practical, to use some techniques that you can use. Again, so if you notice here, negative 4 is going to be a negative number no matter what x is, right? 3 is going to be a positive number no matter what x is. And if you notice here, this is the interesting part. This here has a square root, a cube root, sorry, but it has a fourth power. Remember, fourth power, anything that's even power is going to make this be positive. Always. No matter whether this is a negative number, fourth power, right, the number that is on the numerator, if that's an even number, then this is going to turn this positive. So what I'm saying here is that this is going to be positive. So basically on the bottom part is positive, and on the top part is negative. So negative over positive is negative. So we didn't actually have to check 0 and 3 anymore because we use some logic. So this is going to be negative, 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 negative. So the original function is going to have concave down and concave down. So concave down from negative infinity all the way to 2, and then from 2 to positive infinity. And then concave up does not exist, right? Just to mention that. So there you go. So let's moving on to the next part. Finding where the function is going to be have a local max. Find the location of the local minimum or local maximum. So we already have the two. There's only one critical number. One critical number. Critical number is 2. We already know that that's actually a minimum, right? Because we can see it here. Minimum, right? So it's going to be minimum. So this is actually going to give us a local min, right? So we have a local min. We have a local min at x equals 2, but to find the actual local minimum, we're going to plug in 2. into the original function. And the original function was 6 times x, which is 2 minus 2 raised to the 2/3. Well, we already said this, right? This is going to give us 0. 0 to the third power, 2/3 power is going to be 0. 0 times 6 is 0. So this is going to be 0. So y equals 0. So when x equals 2, y equals 0, and this is your local min, right? The minimum value, local minimum value is 0, and is located at 2. All right. So that's that for that part, and then the next part is to find points of inflection and possible points of inflection and any inflection points. Well, we already found the points of possible points of inflection. That was only x equals 2. That was a possible points of inflection. But is it? Actually, it's not, right? Because there's no change of concavity. This is concave down, concave down. So there's no change of concavity. So that means, by definition, x equals 2 is not an inflection point. Remember that you need to have a change of concavity to have a inflection point. So does not exist, right? Inflection point does not exist. All right. And then the next part is to find horizontal asymptote and vertical asymptote. So let's begin with horizontal asymptote. That means the end behaviors of the function as x goes to infinity. So the limit of 6 times x minus 2 to the 2/3 as x goes to infinity. This is actually pretty straightforward. Why? Because we pretty much, if you replace this infinity here, infinity minus 2 is infinity raised to any power. It's still going to be infinity times 6 is still going to be infinity. So this is going to infinity. Let's try the next one. As x goes to negative infinity. So let's see what happens now. You plug in negative infinity here. Negative infinity minus 2 is negative infinity. Negative infinity square is going to make this positive, right? And so this whole thing is going to be positive. Cube root that is still going to be positive times a positive is going to be positive. So no horizontal asymptote. In other words, does not exist. All right, and then vertical asymptote does not exist because this is defined everywhere, right? There's no number that you can plug in that's not going to make this true. So there you go. All right, so the next thing we want to do is whether there's any x-intercepts or y-intercepts. We already know there is an x-intercept at x equals 2. We want to know whether there's a y-intercept. That means whenever x equals 0. Let's see what we get. Y equals f of 0. This is going to give us 6 times negative 2 to the 4th power, negative 2 to the 2nd power, sorry, is going to give us the same thing as 6 to the negative 2 to the 2nd power raised to the 1/3 power. So this is equivalent to 6 times 4 raised to the 1/3. So roughly, right, just to be able to use this number, it's roughly around 9.552. But we're technically using 6 times 4 to the 1/3. Remember, this is just an approximation. So we have a point 0.6 times or cube root of 4. So let's try that Let's see, where would that be? That would be 9.52 somewhere in here. We already also know there is a x-intercept there. We also know that the function is decreasing, and maybe I'll put this in a different color. It's decreasing and then increasing, and we also know that there is a concave down. So concave down looks like this, and there's a concave down as well here, right? But if you notice, in order for this to be completely only decreasing, as it says in the first part, we can only have this part. And in order for the right side to be only increasing, we cannot have this part. So what I'm trying to show you guys is how you would graph this, right? That means you have to pass through this point, and you have to be in that form. So you have to be decreasing, but in a concave down, and then you have to be increasing, but in a concave up. So this is how it's going to look like. And of course, we're gonna put label our points. So this point is 0, and this point is 0, comma 6 times the cube root of 4. And there you go, right? We found all the